My name is Luis Hernandez. I'm an application engineer with Tektronix, and today we're going to present the real-time spectrum analyzer. Tektronix have been making this kind of spectrum analyzers for like the last 7 years, even though we made spectrum analyzers many years ago, and the regular traditional swept-in spectrum analyzers. But lately we have started to work on these real-time architectures, which are a lot more powerful, and it can provide you more insight on what the signals are doing. So this is a digitizing machine that has a down conversion stage. Then the signal is digitized at that point, and then fully down converted to baseband. At that point, you end up with the INQ of the signal in memory, right? And so we used to do a lot of math on the signal to show you the spectrum, to show you frequency, the spectrum, to do digital demodulation, to show you the time domain of the signal, etc. And that's kind of like a regular or traditional VSA architecture, right? Now, on top of that, we have a lot of features that are unique to the real-time analyzer, and that allows to trigger on specific frequency events and also show you more insight on the signal. And that's the part where we differentiate from traditional analyzers. So I'm going to start by showing you one of our more classical demos where we can see and capture transient behavior on signals that are apparently steady. And I want to show you this signal here that appears to be a signal that is doing nothing. It's just sitting there. It's a CW signal, and time is passing by, and the Maxwell is also telling us that the history of the signal is steady, right? It's just sitting there. So what I'm going to do is I'm going to go through a series of setups to show you what the signal is really doing. By the way, this is updating something like maybe 40 times a second. The traditional swept-in analyzer, the fastest that you will find in the market, does something around 50. That's 50. So I'm going to show you a new display now. So this display that you see on the top is called the spectrogram, and what it does is it shows you multiple spectrum information over time. Right? So the spectrum that you see in the bottom is the spectrum at the point in time where I have the cursor, or where I have the marker, right? So this will be the spectrum at this point in time, and this is the spectrum a little bit before, and so on, right? So you get multiple spectrum information over time. And I just wanted to introduce this display because we're going to be using it on some of the next stages of the demo. And in case it was not clear exactly what this spectrogram is, this is how we make it. This is how we build the spectrum. You got multiple spectrum traces over time, and then we kind of look at it from the top, and we color grade based on intensity. So you can see that the main signal here is kind of wandering in frequency, and that's very obvious when you look at the spectrogram. But if you see one by one, that might be a little hard to realize. Also, you see this little green line here? It's a transient, which is a small, it's a short duration spectrum event, and it's very easy to see in the spectrogram, while in the regular spectrum analyzer view, it would have been just a flash that showed up and disappeared, and very hard to see. Right. So I want to show you now these two displays. The display on the right is the regular spectrum analyzer display. The display on the left is showing you the same signal, but it's using a display called DPX. DPX stands for digital phosphor, and it's trying to replicate the same behavior that the old CRT phosphor-coated monitors used to have. And it does two main things. One is very fast update rates, and the second thing is persistence. So I'm going to show you a slide now to exemplify this a little bit better. I guess not this yet. DPX. So like I was saying before, it's kind of mimicking that property of the old CRTs, phosphor-coated CRTs. So if you see some, in those old monitors, if you saw something brighter, that meant that it was more repetitive, right? So this intensity, level of intensity on the plot will give you information about how persistent the signal was. And the next thing we're doing is very fast update rate. So we're doing actually close to 300,000 spectrum updates per second. The way we build the DPX display is, using the same example as we did before with the spectrogram. Now, instead of looking at the signal from the top, we're gonna look at it from the front, right? And then we pixelate this plane, and then we just count how many hits are per pixel. So, like for example here, this little transient had 2 hits. Maybe if we look over here, we'll find like, I don't know, 7 or 10 hits because there's more activity there. So we end up with a bitmap like this, with a hit count, right, per pixel. And then we color grade, and then, whatever the number is high, we get red. Whatever the number is low, we go dark blue, and so on. And so the color at the end tells you where the signal is spending their time. Whatever you see red, that means the signal spends a lot of time there. Whatever you see dark blue means the signal is barely there. Similar to the persistence that you got on the old CRT codec. And then if we go high resolution, it looks like this. And that's exactly what we were getting on the previous display. So take a look. This still hasn't seen the transient, and this is catching every single time. And what it's telling me is based on these colors, and there's a scale, by the way, that kind of tells you, red means very frequent, dark blue very infrequent, and so on. What this is telling me is that the signal spends a lot of time here because this is red, but we already knew that from here. But it's also telling me the signal spends some time here, but not as much as here, and some time all across here, but not as much as here, and not as much as here. So what the signal is really doing is every once in a while it jumps from this frequency to this frequency. You can see how it overshoots to the right and then comes back and settles, and then returns, overshoots, comes back and settles. Right? So you can see the whole behavior of the signal with this DPX display. The colors then give you an idea of where the signal is spending their time. But we still don't know, for example, if it's spending, 100 microseconds or 1 millisecond, or if it's happening every second or every 3 seconds, right? We just get a relative idea based on the colors. So what we're gonna do next is we're gonna use the rest of the tools on the analyzer to find out all those questions, to get all those answers. All right. So here we see the spectrogram and the DPX display. And we see that this transient doesn't show on the DPX display. And the reason is that the DPX is running in parallel to the main analyzer. And this acquisition engine is also running, they're unsynchronized. So what I want to do next is I want to make these acquisitions when this transient occurs. I want to trigger the acquisition with the occurrence of the frequency event. And to do that, we're going to use this feature called trigger on this. And what it does is it gives me this little box that tells the analyzer, make this acquisition whenever something gets into the box at 300,000 updates per second. The minimum transient that we can capture, the fastest, is about 5.8 microseconds. So I'm going to move this over here. And there we go. Now we're making the acquisitions, in this case, 1 millisecond acquisitions, every time that the signal goes into the box. All right? So if you see this little T here, this is the trigger point. That's the point where the signal went into the box. And if you see, we're triggering on the overshoot to the right. If I move it over here, if I move the trigger on this box, now we're triggering on the overshoot to the left. If I put it right here in the center, then we're triggering somewhere on the transition. And if I put it here, then we're triggering on the signal just being in the traditional position. Oh, okay, that's the same. Let's go to number 7. Okay. Another way that we have to trigger on a signal like this is using a frequency mask trigger. And it's this mask that you see on the spectrum. And what this does is it will trigger, just like DPX did, whenever the signal hit the mask, right? So how do we create this mask? Well, there's a very simple way to do it. You can go to the mask editor, and then you just add points, and then you move the points around, right? Like how we build this mask, for example, you could have gone, just move these dots around, and this tells the instrument, make an acquisition whenever the signal touches the mask. You can also do an auto draw that will just do the mask for you, and you can make it tighter or looser, right? So just close this, go back to where we were. And I want to show how these acquisitions happen. So you can see here when I move the cursor up and down that we are changing the position, the spectrum display in time. And I'm going to go to the trigger position here. And when I get close to the T, you see how the signal hit the mask right there. It's a little too, oh, right there. So this acquisition of 1 millisecond from here to here happened because the signal hit the mask over here. Right? And then, I said that, from the DPX display, we might not get information as, how much the event took to happen or how often it happened. But we can put a delta marker, for example, between here and here. And this will measure the difference in time, frequency, and amplitude. And you can see that the time difference is 260 microseconds. So this whole activity took 260 microseconds to occur. If now I put a delta marker between here and here, now I get the repetition time between these two events, and it's about 1.28 seconds. So what we did here is we acquire a 1 millisecond from here to here, another millisecond from here to here, but between the two there was a whole 1.2 seconds of activity where nothing happened. So nothing violated the mask during that whole 1.2 seconds. There is another mask that will also work. Because the DPX display told us that the signal was going to come over here, then I could do this mask, right? This little dip here. Because I know that the signal is going to go over there, right? So if we see how this trigger happened, again, the T is the trigger point. You can see how the signal swing to the right and somewhere around here hit the mask. There you go. So once again, this acquisition happened because the signal hit the mask. So this allows people building, oscillators or all kind of devices to test for the stability of their signal. So we have customers, for example, that they do parts that are subject to a lot of stress, vibration or heat and cold temperatures, and by doing something like this, let's see, it's taking a little bit to load. By doing something like this, for example, they're able to tell if their signal is taking all this stress and is still maintaining stability. So they're looking for something like this to happen when their part is subject to stress. All right, so I'm going to go to my next demo. And it's about digital demodulation and catching transients on digital demodulation. I need to change the cable here a second. All right, so what we see here is a signal that is digitally modulated. All right, so we see the Constellation, which is the spectrum, and we can see the EVM down here. EVM is a modulation quality metric, and what it shows is that the signal is good. It's showing good metrics. Constellation is good, the spectrum is good, right? Now, once again, we're looking at the spectrum here about 40 times a second. We can actually look at the signal, through time with DPX on a free run fashion. So we're not triggering, we're just going as fast as we can, and everything looks fine. I'm gonna go to my next setup here. Oops. So when we make this acquisition a lot faster, we see that most of the time the signal does look like this, but every once in a while we get this flashy shoulder thing here that is blue, and that blue means that it's very infrequent. Also the fact that it doesn't flash, very often, right? But the Constellation still looks pretty good. So the signal is still good and the EVM is still very good. So it'll be interesting if we could trigger, if we could see the Constellation right when those shoulders show up. And that's what we're gonna do next. I put the trigger on this mark here, and I'll see how the Constellation looks. So we are synchronizing the acquisition over which the Constellation is calculated with the appearance of these shoulders. So we can also go on, for example, look at the Constellation this way. Just look at the points and see how they're all over the place. If we set this to free roam once again, you can see that the points are now perfectly around the crosses. Oh, we just did this. And if we trigger on it, you see they're all over the place. This is the moment when your radio, lost connection or lost connectivity with the transmitter or something. And so what we get here is the same scenario as before, but now we're triggering with a frequency mask. Let this run for a little bit. Right? And so once again, we are triggering this time with a frequency mask. And you can see that the Constellation looks really bad and EVM is really bad because we are doing the demodulation right at the time those shoulders are coming up. We can pause this, and you can see this is good signal, bad signal, and so on. And we're making every one of these little tick areas here is an acquisition. And between them, there could be minutes, hours, seconds. I think this is probably all I had. Do you guys have any questions at this point? On this display over here, on the Spectrum?
On the previous one you showed before.
Oh yeah, absolutely, yeah.
And you put cursors on like the cheaper scopes do.
Yeah, on the frequency domain, or
Yeah,
you can. And one of the neat things about it is that they're time correlated. So when you move it in one domain, it moves in all the others. Let's see if we can do this real quick. I guess when we were over here, so that we were. So when we get this, you can, for example, bring, amplitude versus time. And you can see when you move your cursor here on the time domain, see how it moves also on the spectrogram? We got a couple of cursors here, right? And they're both showing you, the frequency, amplitude, and time of this one versus the same for the other marker over here. And like I said before, they're time correlated, so when you move when you move it in one domain, it moves in the other domains as well. All right. All right. Well, thank you.